Hello boys and girls, so in this tutorial session we are going to discuss on 13.3 molecular kinetic energy and internal energy of gas molecule. So gas molecule move randomly in motions in all directions as we understood from previous lesson. So for any gas molecule that move in motion, they are going to have what we call molecular kinetic energy. So class, since gas molecule keep on move randomly in all directions, when they are in motions, they have root mean square speed, so they are going to have what we call average translational kinetic energy. So translational here actually is referred to linear, okay? They are moved linearly in all directions. So they have translational kinetic energy. So next time when you see translational, it refers to linear. So from previous lesson, we have these equations. PV equal to 1 over 3 N V RMS squared. Then we understood when the gas molecule in motion, they have kinetic energy. So we know that the basic equation for kinetic energy is half mv squared. So how I'm going to relate these equations with the basic equation in kinetic energy? So in this equation, I have 1 over 3. But in kinetic energy, I have 1 over 2. So how I'm going to transform 1 over 3 to 1 over 2? So 1 over 3 can be written as 2 over 3 multiplied 1 over 2. If we write 2 over 3 times 1 over 2, we will get back it to 1 over 3. So class, we can rewrite the above equation as P equal to the volume. I bring it to the right hand side, so I can write it as pressure equal to 2 over 3 N over volume half mv squared. So the terms half mv squared actually will represent our average translational kinetic energy. Alright, so from the above equation 1, you can see very obviously the pressure of the gas is proportional to the numbers of molecules per unit volume and also proportional to the translational kinetic energy of the molecule. So it means that our pressure will increase when our numbers of molecules per unit volume increases, or if the average translational kinetic energy of a gas molecule increases, then our pressure of the gas will increase. Then class, if you recall the ideal gas equations, in ideal gas equation we have PV equal to nKT. So I rearrange the ideal gas equation. I will have pressure is nKT over V. I denote it as second equation. So I might compare my equation 1 just now with this second equation. So I equalize the both equation because both equation actually represent pressure. So I'm going to have 2 over 3 N over V half mv squared equal to nKT over V. Then N can be cancelled. Volume, alright, also cancel. So I rearrange the equations. So class, half mv squared actually represent average translational kinetic energy of a gas molecule. So I can represent this one with K subscript TR. TR means translational, linear. So I get the equation for average translational kinetic energy of a gas molecule. So it's equal to 3 over 2 kT. Then class, K is Boltzmann constant, whereby it's equal to R over NA. So I put it into the equation. So I'm going to have another equations to calculate the average translational kinetic energy for a gas molecule. 3 over 2 R over NA multiplied T. So class, from the both equation, you can see very obviously the temperature is the direct measure of our average translational molecular kinetic energy. Why? You see, R is a constant value. Na is Avogadro number, is also a constant value. So our average translational kinetic energy is solely depends on the temperature. So at a given temperature T, we will find out that all ideal gas molecules, no matter what is their mass, they are going to have the same average translational kinetic energy as long as they have the same temperature. Alright, so how I'm going to calculate the total translational kinetic energy if I have n molecule of gas? This is for a molecule of gas. This one is for one molecule of gas. So if I have a lot, n molecule of gases, how I'm going to calculate the total translational kinetic energy? So we just simply take the kinetic energy for a gas molecule multiplied with the numbers of molecule. Then you will get the total translational kinetic energy. So I multiplied the equations with the numbers of molecule, then I'll get the total translational kinetic energy. So the total translational kinetic energy of a gas is given by 3/2 nkt, or you might have 3/2 nRT. So which one we are going to use to solve a problem? It depends. If you use the numbers of molecule, then you have to use Boltzmann constant. If you use numbers of mole, then you are going to relate it with molar gas constant. Clear? So guys, bear in mind, molecule of gas that move randomly in space, they are going to have what we call translational or linear kinetic energy, which we can calculate using the equation below. Alright, anyhow, bear in mind, besides the translational linear kinetic energy, actually gas molecule can also have kinetic energy due to the rotational and vibrational motion. Okay, so later on the next video, we are going to see how the rotational and vibrational motion will contribute to the kinetic energy for a gas molecule.